potential energy, gravitational potential energy, and that would be equal to Gm1 m2 by. This is the thing that we got in the previous class, right, guys? So potential energy arises due to the interaction between two masses, right? Gravitational interaction. And the due to gravitational interaction, the energy is stored in the form of this potential. So this we did in the previous class, and we require two masses only, right? So then we were doing this problem. So we were doing this problem, and we needed to find out how many gravitational interactions are there, right? So we found out that there are 6 interactions, right? So let us calculate what would be the total potential energy of this system. Okay, so let us calculate that. So I will write all these are m. So let me write it so let me write it. We have 4 masses, equal masses, kept at the vertices of a square. And we have to find out what is the total potential energy. This length is L, right? So we found out that there are 6 interactions. 6 interactions or 6 combinations, right? So first we counted from this one, we required 2 masses. From A we counted, and we got how many? From A we got this one, and this one. So U at A has 3 contributions, right? Plus, then we got from this one. So how many contribution we got from here? So from this one I have 3. Yeah, this one I have already counted, right? AB. So this one and this 2, right?
Yes, sir.
And then the last one was which was remaining was this one. So at C, right? So this one I have counted, this one I have counted, this one. So this one is only, right? So U C was as one. So now let us separately write all these values. So first between UAB, then we have UAC, then we have UAD, and then you have UBC, then you have UBD, plus you have UCD. right? 1, 2, 3, 4, 5, 6. Is that clear, everyone?
Yes, sir.
So UAB, I have taken two masses U, A and B, right? Separation is L. So what would be potential energy due to UAB? What would be the potential energy? Masses are M, M, separation is L. So what is the potential energy? Yes, guys, this we already know, right? This I have told you guys. So what would be UAB? What is M1 here?
M.
M2 is what?
That was M.
M and separation is
M separation will be 1 by M minus 1 by M.
A to B. What is the distance between A?
L.
L. So simply minus G M1 is M, M2 is M divided by L. That is the potential energy, right?
Yes, sir.
Similarly, what would be A to C? This length we don't. But I know that this is L, this is L. So how much would this length be? How much would be this length? AC would be how much? This is
Root 12.
yes, correct. So root of L square plus L square, which is root. So this AC separation is root. So what would be the potential energy? Yes. What would be the
Minus
potential?
G. L. L.
Mass. What is mass? L
There is
is
no mass.
M. M, right?
Okay.
Why there would be L in here? Separation is root 12, right?
Yes, sir.
This is 2AC. Now what is AD? You guys tell me what is AD?
Minus G mm by L.
Minus G by L. So is that correct, everyone? And now, what about you guys? What do you guys think? Is that correct?
Yes,
Yes.
sir.
Okay, good. So why you guys are not replying? Okay, then we have to find this BC. So what would be BC? Yes,
Same minus G mm by L.
mm by L. Good. And BD. What would be BD?
Minus G mm by root 12.
And then last one CD. CD would be again minus GMM by L. So these are all the potential, right? So minus GM square by L minus GM square by root 2L minus GM square by L minus GM square by L minus GM square by root 2L minus GM square by L. So 1, 2, 3, 4 minus 4GM square by L, and there are 1 and 2. So 2GM square by root 2. This will cancel this is right. So then what we will get? We can take minus GM square by L common, and this would be 4 plus So this is the total potential energy. Is that clear, everyone?
Yes, sir.
Please note it down. And if you guys have any doubts, please note down this. Yes, whenever you guys have noted it down, please. Yes, whenever you guys have noted it down, please.
Finished, sir.
So what about you, Elham and Amna? What about you guys?
Done, sir.
Next topic is gravitational potential, right? So if we move one unit mass from infinity to a fixed point, so in the previous case, right, in the previous case, what did we do? We move the mass m, right, from infinity to a fixed point r, and that we call the gravitational potential energy. But if we take a unit mass, which means that we divide this work done by this unit mass m, then whatever the result would be, so that would be called the gravitational potential. So this gravitational potential is Gravitational potential. So this is work done in bringing a unit mass from infinity a fixed point r by the gravitational force. Right. So we have to simply divide this. So if you want to calculate the potential, we simply divide it by the mass. Right. So this would be minus g m e and m by r divided by. So this m will cancel and this would be simply minus g m e by r. So that is the potential. Okay, is this part clear? So if we have, let's say, this earth, right? This is the earth and we are calculating the potential at this point. So this would be due to the single mass of the earth. And that would be simply minus of g me by whatever this distance r. So that is the gravitational potential. Is that clear, guys?
Yes, sir.
So let's say if I have this mass, right? This is the mass that I have, and I'm calculating at this point P. So potential at this point P, and the separation is R. So that would be simply, I don't require the other mass here, right? I don't require any other mass in here. I only require one mass. And that will create some potential around its space. So that would be V at P, that would be minus G M divided by. Is this clear, guys?
Yes, sir.
Okay, so we will do one question, which is exactly the same question, but we will calculate the potential at center. So we'll have to calculate the potential at center, and yeah, so we'll do that, but you guys please note down this. You guys note down this part and then you'll do that question.
Okay, sir.
Yes. Whenever you guys have notes, it down.
Finished, sir.
Finished. Elam and Amna, what about you guys?
Done, sir.
Okay, so now let us do this question. So same question, but we have to calculate the gravitational potential. And yeah, so we have these masses. And because we need some point to calculate the gravitational potential, right? So in the question they have told us to calculate the gravitational potential at this point. This is point P. This one has mass m. 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 This is L. This is L. This is L. This is L. So if I want to calculate the potential at P, how many contributions would be there? How many?
6.
6. What are the 6 contributions?
So from where you're telling? A, right?
We are calculating the potential at this point. Vp. So Akib is saying we will have 6
4.
contributions.
No, now it
4,
changed 4.
4. So 4.
4,
Amna is saying 4 and Ilham is also saying good. So we will have a 4 contribution, right? Only 4 masses are there, so there will be 4 contribution of potential. Good. So yeah, so there would be 4 contributions. And all those contribution would be VA plus VB plus VC plus VT. Because potential is a scalar quantity. So this we can add algebraically, right? If we had if we had to calculate the Newton's force of gravitation, right? That would have been problematic because if they told us to calculate FP, so in that case we have to use this one, right? Right. But
Yes.
this potential is a scalar quantity. This potential is a scalar quantity, then we'll just algebraically add. This we have to keep in mind. Okay. So VA is, we are calculating the potential at this point due to A. So this is the separation, right? How much is that? You guys have already calculated that total is root 2L. So this would be half of that, right? Right, guys?
Yes, sir.
So VA would be minus GM divided by root 2L by. Similarly, VB is how much? Minus GM L by 2. And
So should it be minus gm square?
M square, where is M square? Why is M square? We are not calculating the
No, okay,
potential.
understood.
Yes. So, yeah. And minus GM divided by 2L by. Good. So then this is minus GM. 2 is in the numerator and root 2. This is root 2 minus Gm. I will write again root 2 divided by L minus G root 2 divided by L minus Gm divided by L. So this is 4 root 2 Gm divided by L. So this is the potential at. Is this clear, guys?
Yes, sir.
Okay, so please note it down and this part you guys can put it, right? This part. Yeah, whenever you guys have completed noting it down, please.
Done, sir.
Yeah, okay, 1 minute. One moment, please. Yeah. Okay, so electric potential is done. Now we have three topics which are so one is this escape speed. Then we have this orbital speed, and then we have this energy of this system. Right, so these are the things that we have to calculate. But to derive or to calculate these things, we have to remember that, yeah. So let's say this is the Earth, right? And we are, let's say, here. Let's say not we are, but something is here at certain height above the Earth's surface, right? And we want to escape from here, right? So let's say we will have some certain potential energy. So this is H. So what would be the potential energy, guys? What would be the potential energy?
mgh.
Not the MGH. That is the, yeah, so MGH would be there, but that is the approximated case. What is the actual potential energy? Potential energy that just now we have done. Minus GMEM divided by R plus H. This is the potential energy, right? Right, guys? Yes, sir. Is that correct?
Yes, sir.
So this means that if I am here, Earth is pulling me down with this much of energy, right? With this much of
Yes.
energy, the Earth is pulling me down. And if I provide some certain kinetic energy, right? If I provide some velocity, right? So then I will have, let's say I project myself or I throw something from here with some velocity v in upward direction, right? So then the total energy would be how much? That would be kinetic energy plus the potential energy, right? So that would be half mv square minus of gme m by r plus h, right? This is the total energy, correct?
Yes,
So
sir.
yeah, so this part is making me go upwards, right? This part is making me go upwards, and this part is pulling me down, correct?
Yes, sir.
So let's say I throw it with, let's say, 2 meter per second, right? So it will go upward and ultimately it will come back again. It will come down, right? And let's say again I throw this with, let's say, v equal to, let's say, 5 meter per second. So it will go again upward, and ultimately due to this term it will again come. But let's say I provided that much of a minimum velocity so that it reaches this value. So this value becomes this value, right? Then I'll be
Yes,
out
sir.
of this Earth's influence, right? Right?
Yes, sir.
So then the minimum velocity I would require, right? So minimum velocity I would require to achieve or to escape from this Earth, that would be equal to this one. So my total energy becomes 0. So if I put it equal to 0, then this is V minimum, right? Minus of G M E M R plus H. So this is half M V minimum square, and this is equal to G M E M divided by R plus H. So this M cancels, and I will have V minimum square, that is 2GME divided by R plus H. And let's say I'm throwing this object from surface, then H is 0. So at surface, H is 0. So this will become how much? V minimum is root 2 of GME by, right? So this is this is G, right? So this is G. And how this GME by R related to G? What is G? What is the value of G? You guys remember?
9.8.
No. So I'm asking in terms of GME by R. What is G? This is GME by R square, right?
Yes, sir.
So then I can put the value of GME. I can put the value of GME as GR square. So this would be root of 2 GR square divided by R. So this will cancel. And this is the minimum velocity, which is also called escape velocity. This is equal to root of 2GR. So with this much velocity, minimum this velocity I require so that I can throw this object out of the surface of the sphere and it will not return back. So that is the idea of this escape velocity, right? So escape velocity is what? Escape speed. So the minimum speed required to be thrown by object so that it reaches beyond the influence of Earth's magnetic uh, gravitational pull, and it will not come down. Right, so that would be the escape velocity. So let's say if I throw this object with the minimum escape velocity required, so it will go out of this Earth, right?
Yes, sir.
That is all about this escape velocity, right? And if we calculate the escape velocity of the Earth, so that would be how much? V escape for Earth. This is root. G is 9.8. R is how much? 6,400 kilometers, right? So 9.8 meter per second square. So this 6,400 kilometer is 1,000, right? So let us write it in meter per second, right? So this is this. So this would be how much? So this is 9.8 into 2 into 64. How much is that? And then we have this 2, and we can take the outside. So this is 110 and then other 10, right? And then this is 2 into 98 and 60. So how much is this? Well, and then we take the root of this is 100 and 12,544. So how much is the root of this? I'm just showing you guys that how much with how much velocity we should throw an object so that it never returns, right?
Yes, sir.
This is 1,544, 1, 1. With this much velocity, we have to throw the object so that this never returns, right? So this is how much? 11200 meter per second, which is 11.2 kilometer per second. You have to throw an object with this much, you are on the surface. If you throw the object with this much velocity, then it will never come. Okay, so you can try this thing, right? At your home, on the roof, you just stand and then throw the object with this much velocity. So is this clear, guys?
Yes, sir.
Please note it down. And if you guys have any doubt, please ask. So the idea of escape speed is that we have to provide the minimum velocity so that it covers the potential energy. So kinetic energy becomes equal to the potential, right? In that way, we can achieve this escape.
Can you scroll?
Yeah. This is V escape for like, yeah, whenever you guys have noted it down, please,
Done, sir.
okay, so Akib and Amna, what about you guys? Noted.
Yes, sir.
Yes, sir.
And yeah, so did you guys understand that why this is becoming zero, right? Why this is becoming zero? Because initially we had only this total energy was only this potential energy, right? So energy was negative, and we are providing a positive energy, kinetic energy. So then the energy is increasing. If we are increasing the kinetic energy, then this energy is negating, right? And then this energy is increasing, so this total energy is becoming nearly to zero. When it reaches zero, then this all this potential energy has been changed into this kinetic. So then we got this escape velocity, right? So that is why this is zero. Okay, because initially the energy was negative, and this negative energy, this is the pulling energy, right? This pulling energy we have to overcome, which means that we have to provide some positive kinetic energy. So that we provided, and then we got this. Okay, so the next topic is Earth satellites, right? Before we do the satellite, so do you guys remember that if something is moving in circle with v velocity, so what is the force that is acting towards the center?
Centripetal force.
Centripetal force. Good. So we will remember this thing, right? So this centripetal force is provided by different things, right? So in the case of this frictional force, in the bending of roads, we saw that the friction force was providing that centripetal force, right? Right, guys?
Yes, sir.
So, and in some other cases, we saw that the tension was providing that centripetal force. So, remembering those things, now we will see that what force is providing the centripetal force, right? So, we have this Earth and some satellite is rotating this Earth. right? This is H and this is R. This is rotating. So what is the force that is providing this centripetal force? What is the force that is providing the centripetal force? Guys?
Gravitational.
Yeah. So gravitational force of attraction, right? Because this Earth is pulling this satellite towards its direction, right? But it is moving in circle, so there must be some force which is acting towards the thing. So the centripetal force is provided by gravitational force. This is the thing that we have to remember, right? So we have F centripetal that is equal to Fg. So how much is this centripetal force? How much is that? If this has a mass m, so what is the centripetal force? What is the centripetal force of this satellite? Centripetal force is mass into acceleration. What is the centripetal acceleration? We have just done the uniform circular motion after.
Yes, sir.
What is the centripetal force?
I don't remember.
Guys, please revise. Uniform circular motion. This thing, centripetal acceleration, we should always remember this thing. So this is mv square by whatever the distance is. So r plus h. Right, everyone? Is this clear?
Yes, sir.
And yeah, then let me write this one here. So centripetal force is mv square and that is the centripetal force. Now this one you should, what is the gravitational force between mass of the earth and the mass of the satellite? What is the gravitational force?
Mg.
Gravitational force G. Gravitational force between two masses. Newton's law. This is the gravitational force, right?
Okay, sir.
So G M E M divided by this is the separation, right?
Yes, sir.
Okay. So this speed is called the orbital speed, right? So this orbital speed would be how much? So in escape speed, you guys have to remember that we have to work against this potential energy, right? So kinetic energy we have to provide. So that is escape speed. In the case of orbital speed, we have to remember that centripetal force is equal to this gravitational force. So these two things we have to. So if you want to calculate v square, that would be g mass cancel. So me and r plus h divided by r plus h square. So the square will cancel. So v orbital, this is a root of gme by r plus h. Right. So this is the orbital. And if we are at the surface, so at surface some satellite is orbiting, which is not the case, but at surface what would be the orbital velocity? So at surface h is 0, so orbital velocity would be of gme by r. So we know that GME is gr square. So this is cancelled. So this is p orbital is root gr. So you saw that escape velocity was root 2 gr. Escape velocity was root 2 gr, and orbital velocity is root gr. Okay, these are
Yes, sir.
this is the Earth satellite, and we can also calculate the time period. So time period of oscillation or revolution. So how much time it takes the satellite to cover one full rotation of the Earth. So how much would that? We know that V orbital is how much? That is root of g m e by r plus h. So this is the orbital velocity, right? And then in
Sir,
yes,
instead of writing this, can't I just write G into R?
yes, that would be at the surface, right? But the satellites are at some heights. They're not at the
Okay,
surface.
sir. Okay.
Depending upon the question, we can use right. So depending upon the question, whether they are telling us that no, we are taking the Earth's surface, or we are at some, or the satellite is at some certain height. So depending upon this. Okay. Yeah. So this is the orbital speed with which this satellite is rotating. This is Earth, right? And this is r plus h, and this is the speed with which it is rotating, v orbital, right? In one full rotation, how much, what is the angle that it covers? What is the angle?
360?
360, right? So in a full 360 rotation, it covers 2 pi, right? 2 pi angle. So
Yes, sir.
then, yeah, so then what would be the, so t would be, let's say this is, right, distance is 2 pi and r plus h, right? So this is the distance it is covered, 2 pi r plus h, right? Total distance is how much? 2 pi r plus h,
2 pi.
right? 2 pi r. So this is 2 pi r, and in our case, r is r plus h. This is the total distance divided by the velocity, right? So that
Yes, sir.
would be the time. This would be how much? So this is 2 pi r plus h, and v orbital. We can write this as root gme by r plus h, right? So this we can write as pi r plus h, and this goes in the numerator. This is power half, and then root of Ga, right? So then this would become how much? So this is 2 pi r plus h, 3 by 2, and root G. So yeah, and we can write this GME as GR square per. So this is the time. But let's say if we are calculating at the surface, so at surface, h is again 0. So this is called T naught, which is 2 pi r 3 by 2. And GME is how much? GME is GR square, right? So this is 2 pi and this is R3 by 2 and minus of 1 divided by G. Then this would be how much? This is 2 pi and so then this is 3 by 2 minus 1.
1 by 2.
So 1 by 2, right? So this would be root R because this numerator is R by 2, denominator is G by 2, right? So I can write as R by G. Is that clear?
Yes, sir.
So this is called the time period of water. Okay. And so this is about the orbital velocity. And did you guys note down this part? We have not noted down, right? So let us, you guys please note it down and then we'll do the energy of the particles. So if you guys have any question, please ask. Yeah, we'll do all
No, sir.
some questions to understand it. But you guys have just remember for the case of escape speed, we have to calculate the energy, kinetic energy, potential energy. For the case of this orbital speed, we have to calculate the centripetal force and the gravitation.
So can you scroll?
Yes. Yeah, so whenever you guys want me to scroll down, you guys can.
Done, sir.
Done. Okay. So time period of time period when this satellite completes one revolution. So in one revolution, it covers how much distance? It covers 2 pi r distance. R is r plus h, right? This distance it covers, and velocity or speed is this one, vr. So then we calculate the time, right? Distance by speed. Yes, whenever
Done,
you
sir.
can. Yeah. Yeah, completed everyone?
Done, sir.
Now let us calculate the energy of the satellite, right? So satellite has some orbital velocity, and this is the last topic, energy of satellite. Okay. We have Earth, and this is the satellite which is rotating with, let's say, v orbital velocity, and right. So this is r and this is h, and what else do we have? So this is Earth, and this is the satellite, right? So now, what would be the energy of this satellite? What would be that? Can you guys tell? What would be the energy of this satellite, guys?
Both potential energy and kinetic energy.
Absolutely right. So it will have kinetic energy plus the potential energy, right? Good. So it will have these two things. So let us try to calculate what is the kinetic energy. So kinetic energy, before we do that, potential energy we can directly write. Potential energy we can directly write. So what is the potential energy, guys? Yes,
My
minus
minus ME.
G. Where is G?
Yeah,
M
sorry, G minus G MEM
M
by R square.
R is square
Sorry, R plus H.
R plus, right? This is the potential energy, right, guys?
Yes, sir.
Okay. And kinetic energy would be how much? This would be R m v orbital square, right?
Yes, sir.
So how much is this v orbital? How much is this? This is m, and v orbital is, we have calculated,
Root of.
root gme by r plus h, right?
Yes, sir.
So root gme by r plus h square. So this root will vanish, right? So this is half m g m e r plus h. Is that correct, guys?
Yes, sir.
So let us write it appropriately. So this is half g m e m divided by r. This is the kinetic. Now, as we know that total energy would be half sum of potential energy. So total energy would be potential energy equal to kinetic energy plus potential energy. So this would be half G M E M divided by R plus H minus uh, this is G M E M by R. Right, guys?
Yes,
So
sir.
we can take a common G M E M by R plus H. We can take common. This is half minus 1. So what is half minus 1?
Minus half.
Right. So this is minus half G M E M divided by R plus H. So this is the total energy of this. This minus sign is representing that it is still bounded, right? Bounded, that it will not go away from the Earth's influence. So it is still under the Earth's influence, right? Because
Yes, sir.
total energy is negative, which means that this satellite is still under the Earth. So if it goes beyond the Earth influence, then it will not return back, right? So
Yes, sir.
yeah, this was the final topic of this chapter, and this chapter was easy, right? Guys, please note it down and let me see what question. Please note down this part.
Okay, sir.
Yeah, whenever you guys want me to scroll down pages.
Second is correct.
Yes, whenever you guys have noted it down, please.
Done, sir.
Yeah. Yeah, Ram and Maki, what about you guys?
Done, sir.
Done, sir.
This question is, you guys just revise these portion and we will do these questions in the next class. But today I will just talk about what we will study in the, yeah, in the next chapter. What next chapter is about this is mechanical properties of the solid. And the first topic is elasticity. And next one is we have different molecules. Only two topics are there in this chapter. You have these solid objects, right? And you apply some force on this object, then it will deform, right? So chapter name, yes, chapter name is mechanical properties of the solid. Chapter is chapter 10. Oh, 9, chapter 9. Yeah. So we will see that, let's say you have a spring, right? So you have a spring, and what you do is that you stretch this spring in two sides, right? So it will be stretched, but if you remove this force, then it will again come back to its original, right? Because this spring is elastic. So whenever you have a material which you deform, right, and it will again come back to its initial state. So those kind of materials are called as elastic materials, right? But let's say if you have some material and you deform them by applying some force, and they can't go back to its original position or its initial state, then those kind of materials are called plastic, right? So on the basis of deformation, you have those two objects, materials, elastic materials, plastic materials. And yeah, and we'll see that. So there is this stress and strain curve, and this is elastic curve, and in that we will see that there are different kinds of points, right? So those I will tell you guys about. And in that, and that after that, you have these models. right? So you have three kinds of modulus. One is this Young's modulus, and then you have this shear modulus, and then you have this bulk modulus. So let's say if you have this cylinder, right, and you are applying the force in this. Let's say you are applying the force in this direction. So it will stretch, right? So in this case, you will only have a change in length in this direction. Only one direction you will have this change. Let's say initial is this. So after that, this would be delta, right? So this kind of stress will give you this Young's modulus. And let's say if you have this surface and you are applying the force in this way, then it will deform in this way, right? So this kind of modulus will give you this shear modulus. And then you have this liquid, right? So you have this liquid and you're applying the force in every direction. So then this kind of thing is called the bulk modulus. We will see that what are these. So we will see that what are these strains and what are these stress. Depending upon those stress and strains, we will have these modulus, right? So next class we will do that, and it will only take one class to finish this chapter. We will do that, and in the next chapter we will have these fluids properties. So this solid property would be very easy for you. This part you guys will understand quickly, and then we'll talk about the properties of the fluids. So that will not take that much time. But in the meanwhile, what you guys do is that you guys recap system of particles and this gravitation. That is very crucial. Okay. Yeah. So,
Yes, sir.
but this chapter is going to come for 10 marks. Yeah. So because the question would be on these topics. These are main topics. And very important. So these are main. And then you have this curve. So this curve is also important. This is yeah, so stress versus strain curve. And we will see that this question will come sure. I'm very sure that they will ask this question. This one is very important, and we will talk about this stress and strain curve in next, right? Yeah, fluid is going to come in 20 marks, so that is also a short. 20 marks for fluid and 10 marks for this solid. And how much for the system of particles and gravitation? Those will have those big chunk of marks, right? 10, 10. How is that possible? System of particle is the biggest chapter. Gravitation is the smaller chapter, but as compared to this solid and fluids, that is a very big distribution of marks, if I say, because yeah. So they are focusing on this fluid part. Why? Okay, so we will stop it here, and the next class we'll talk about this properties of this solid. Okay, and you guys have
Okay, sir.
yeah, you guys have this class assessment, so please take that test. Okay, guys.
Okay,
And
sir.
yeah, when you guys